displays. I'm just trying to make it mirror. Yeah, I'm just trying to make it mirror.
Great.
Sorry. Keep changes. Cool. No. Yeah. Okay. So good.
I don't know. Okay.
Okay.
Thanks. Okay.
So today I am going to be telling you about how SSA is secretly Freyd categories. So building on the theme of everything secretly being categories. So I'm going to begin, for those who don't do compilers in the audience, a quick review of what SSA is. So SSA stands for static single assignment. Here's a program for computing Fibonacci. It does, roughly what you'd expect it to. This program is 3-address code, but it is not SSA. Why is it not SSA? Because we assign to M there, but we have previously assigned to M there. So, it's not a single assignment. Same for N. And it's also not SSA here because I has, some previous definition. Maybe we inherit it from the environment as a parameter, but we're redefining it. However, this is fine because even though that statement is going to execute multiple times, T only has one definition. And SSA is about the number of definitions, not how often they execute. So just keep that in mind. So let's transform this to SSA. So how do we transform this to SSA? We just need to number how many times the arguments appear, and we need to add some arguments to our basic blocks. And now traditionally, SSA is done with phi nodes instead of arguments to basic blocks, but that's about the same thing. They're in bijection. So we're going to ignore this distinction and use arguments because it is easier to give semantics to. So why would I do such a thing? Why would I write my programs in SSA form? Well, everyone uses them, so I should too, right? Just like if all my friends jumped off a bridge. So classical compilers use SSA. MLIR, which is mid-level intermediate representation, uses SSA for all kinds of cool things. We use it for GPUs with SPIR-V. We use it for CPUs with LLVM. We use it for FPGAs with the CIRCT project. People are even using it for quantum computing. So that's kind of crazy. Why? Well, it's easier to reason about variables. So you could do fun things like, strength reduction, scalar replacement, constant propagation. It's also way easier to compute your dependencies, which lets you do data flow analyses and fun stuff like that. So what does it mean by easier to reason about variables? Let's be precise. Let's say we have this little program here. Well, since I know that x is always going to be add yz, and I know that add yz is a pure operation, I can just substitute the value for x. That's always valid. And now I can, do a little bit of algebra. Now I could just get rid of y, get rid of w. And that all just works, and I can use this when I'm writing an optimization pass, which is really nice. So the key feature of SSA is that I can do substitution, which, should be ringing some bells here. The other cool thing about SSA is I can do dependency analysis, right? I need to have state edges for any stateful operations like printing, whereas, stateless operations, their dependencies are only their arguments. So it's really nice because I can just generate this graph. I can literally just read it off my program text. So it's great. But of course, here we do dogma. And the dogma is that if something is widely used, it must have an underlying categorical structure. What is this not true, right? So as examples, string diagrams are, of course, always monoidal categories every single time, except the semi-monoidal cases. Then STLC is always a Cartesian closed category. Effects are always monads, except when they're not, because sometimes call by value is a Freyd category. So what's a Freyd category again? Well, we get a Cartesian category, monoidal category, and we've got an identity on object functors from the Cartesian category to the center of the premonoidal category that preserves all premonoidal structure. So what does all that nonsense mean? Well, a premonoidal category is like a monoidal category, which, typo there, except that this guy, instead of being a bifunctor, is just a regular functor. So in each parameter. So what does that mean? It means that sliding doesn't hold. And if sliding does hold, then we say morphisms in the center. Okay, what does that mean as an actual diagram? It means this is not true anymore. So how do we represent that this is not true anymore? We draw more lines. And if something is in the center, then it is true. And therefore, we could just kind of remove the line. I hope this looks awfully familiar, right? So call by value, notation, types, contexts, obvious semantics, obvious categorical semantics is obvious. What's this P here? So that P is going to determine whether we're in C0 or C1. So C1 is the pure stuff, C0 is the impure stuff, right? So a variable can be either pure or impure, and it's just going to take the appropriate projection. And we just define that little downgrade operator that says a pure thing can be used as impure, but not vice versa, right? Glossing over. And an application is, exactly what you expect it to be. Our operations are going to be modeled as morphisms, and we just apply it to the appropriate denotation, and off we go. Now, so again, I should have probably mentioned that we're modeling the definition of an expression as a morphism from the denotation of a context to the denotation of the term. So how do we model products? Well, we model products using the underlying Cartesian structure, and we are going to require that products are always pure. Why are we going to require that products are always pure? Because there's no implicit execution order, right to left, left to right, I don't know, so we're not going to specify it, and therefore it needs to be pure. And finally, we have projections. Okay, that's great. So now we have our first little theorem, which is downgrade, that says that any pure term can be treated as impure, and semantically we want that operation to hold. Okay, so far so good. Now, what's a basic block? Well, if we can interpret a basic block as a morphism that is impure from the set of live variables on the input to the set of live variables on the output, because the empty basic block, right? Can be viewed as just dropping the variables using the Cartesian structure that we don't need. Whereas on the other hand, if we have a let binding in the basic block, that just lets us add an additional variable by first off computing A and A and then moving on. And so all of these are morphisms in C0 because A and A is potentially stateful. So notice that's a 0. So now that we've given a categorical semantics for basic blocks, right? It's just a morphism from the live variables on the input to the live variables on the output. Oh boy, time, right? So that's great because now each one of these blocks in our control flow diagram can be treated as a morphism. But how do I actually draw a control flow diagram so I can do SSA? Well, we need some kind of symmetric monoidal structure. So we're going to pick the simplest one that lets us do this, and that's coproducts. And that lets us do this, which is really nice. Okay. So specifically, what I want to do is I want to add a judgment that says that the entry block goes to either the left or the right with live variables gamma on entry. So that's what the diagram is going to look like. So we're going to need to add label contexts. So label contexts are just going to be pairs of a name, a context, and a parameter type. They have the obvious denotation. And now gamma says that T goes to L is just going to be a map from gamma to L, and that's what it looks like, right? Gamma is the live variables on the input, and it goes to one of the outputs. Okay? So now we can talk about branching. We have an unconditional branch, which does exactly what you think it does. So notice I'm just going to say that if we can reduce the set of live variables and the label and parameter are the same, then that works. And we have a conditional branch, which is an if. And once we have that, we can write our SSA programs with a little bit of syntactic sugar. Okay, so now we can do a tree, but I don't want to do a tree. I want to merge the tree. So how can we merge the tree? Well, I also want to be able to write loops, like our little Fibonacci program. So we are going to have to be a little bit more clever. So how are we going to do that? We're going to introduce an LGOT structure, because of course we are, right? So what is an LGOT structure? Well, if I have a morphism from A to B plus A, I want to be able to take its fixed point from A to B. So I want this to actually be a fixed point, and I want it to satisfy some nice properties. So these nice properties, look like mathematical nonsense, but they're not that complicated. So first off, is a fixed point is actually just going to be the same thing as a trace, right? Specifically a trace with the join operator at the top, the coproduct join, right? And once we view that, then the fixed point definition just basically says it is actually a fixed point, which is nice. And then the other axioms are essentially geometric. So here we have naturality, which just says that G can be pulled out. Here we have codiagonal, which is essentially just saying geometrically that one of those joins can be pulled down under the F. And finally, we have one of the most important theorems, which is uniformity, which basically says that that H can be pulled in front of the F infinitely many times, quote unquote, inside the loop. And this justifies all kinds of fun optimizations like, loop hoisting and all that fun stuff. So now that we know that, we have two choices. We can view our program as a collection of basic blocks, where a basic block is just going to be a set of instructions like before, followed by a terminator. Or we can just allow a bit of a generalized SSA and just allow, sticking instructions in front of the terminators, making everything a tree. Now that's a strict generalization, so we're going to do the recursive one since it's easier to reason about. And finally, we're going to introduce our cleverest and dumbest gadget yet, which is, we want to have general graphs. We need a good way to do the graph, so we introduce the where block. So what does that mean? We have an entry basic block T, which is then going to go into W, where W is a collection of basic blocks. And then finally, once we go into our collection of basic blocks, we're going to exit. So the empty collection of basic blocks is just going to be the identity, because that means that anything we call in T can't actually be inside the where block, so it needs to be outside. And when we add something to W, we are going to, when we add something to W, we're going to put it through this gadget. Okay, this again makes no sense, so I'm going to draw another picture. So what am I saying? I'm saying that if W contains K and then the label L, I'm going to take my L here, right? And I'm first going to calculate K, and otherwise, if I branch to the label L, then I am going to calculate the definition of the label L, and I'm going to merge that and go through. Okay, that probably still makes no sense. So here's a concrete example. Consider the where block with two labels having two definitions. And so the inputs are going to be L0, L1, and L2, and the outputs are just going to be L0. So what's that going to look like? Let's say I call L1 inside the where block. Okay? So now I'm going to execute T1. And let's say that T1 calls L2. So now I'm going to go down this wire, and the next iteration I'm going to appear up here. And let's say L2 returns by calling L0, which is going to be our output. So now that's going to go down here, and then the next iteration we're going to go out on L0, and we're done. So we've just implemented iteration. So make sure our models make sense. We have lots of concrete models. So a monad is LGOT if its Kleisli category has an LGOT operator, and lots of common monads are LGOT. So we've got result as well as option. We've got non-determinism. The state transformer of an LGOT monad is LGOT, the reader transformer, the writer transformer. And so in our paper, we actually give an LGOT monad for non-deterministic and potentially infinite monoidal. And this lets you reason about all kinds of things like printing, heap access, and TSO-style weak memory that I wish I had time to talk about. And now that watching all the previous presentations, realized it would have been a better topic for GALOP', but alas. So yes. So what's the point of doing all this is that we can do things like substitution of pure terms. And we can do in-place rewriting of impure terms, and as well as other kind of control flow optimizations, and we can justify them all categorically. So that means that if I want to, develop a model for my SSA, and I want to make sure my optimizations work on it, I have this clear categorical API that my model needs to implement. And as long as it implements that API, we're good. The optimizations are valid. So future work. All of those typing judgments I showed you before require that all names are unique, which we do by alpha conversion. This is not compositional. This is really ugly. And trying to formalize this in Lean 4 has made me cry blood many times. So we're trying to fix this. Work in progress. Also, that where construction is nasty. Thankfully, I've been working on a better one as part of these formalization efforts. And finally, we want to support regions, because once we support regions, then we can talk about MLIR. And if we talk about MLIR, then we can do cool things. And finally, I want to formalize all this stuff in Lean. We're about halfway there, so that's fun. Any questions? Hydra's laughing. That's not a good sign.
Any questions?
Yeah, cool.
I will ask a naive question. So, what's the benefit of proving it's a Freyd category?
What's the benefit of using categories?
No, not using, but proving that it is a Freyd category.
So the benefit here, right, is that that's a very common structure, right? Like we said before in our concrete model slide, it appears literally everywhere. And it's not too hard to take a model and prove it's a Freyd category. And so now that I know that all these optimizations work on Freyd categories in general, and also that I can take advantage of algebraic identities from the underlying category, I now have a way to take my SSA and generalize the optimizations to a new model. So the real thing is, so for example, in MLIR, they have an abstract SSA that works on many different things, FPGAs, GPUs, and they provide an interface of things like, for example, commutativity rewriting that lets you implement your optimizations using that interface on the abstract IR. So what we want to do is formalize this, and basically, so a compiler engineer is going to say, my model satisfies this interface, so therefore I can do this MLIR optimization. What we're doing is just translating that into mathematics and saying, my model is a Freyd category, so therefore I can do the basic set of MLIR optimizations. And of course, later on, we want to find out what's the categorical structure underlying the more advanced ones, and we want to support things like regions, hence that bit in the future work. So we're basically just categorifying what MLIR does, and Freyd categories just happens to be the way to do that. Like, they identified the structure, they didn't give it a name, now we're giving it a name and trying to figure out what it is in the literature, basically. So much like you were talking about the kernels, actually, how like they already found the structure, they know about linearizability, we just need to find out what they were talking about.
That's it.
I mean, I can speak up if there are people. Okay. So now that you have a structure for compiler optimizations, have you also been looking for dual structures, sort of?
What do you mean by dual structures?
So, okay, I can recognize in my graph that, oh, here I can do constant propagation folding, and I suppose in your category you have some structure and a rule about that, right? So, and then usually when you have such a construction, you can find a dual construction, right? Sort of.
Well, I mean, we're using a lot of, I'm not sure what you mean. Like, are you looking at like if I took my category and I just inverted it, what kind of structure would that be?
Yes, it's sort of. Can we learn something about the compiler optimizations that we didn't already know from your category, or is it just a different way of formalizing what we already know?
I think it's just the key is not that it's a better way of formalizing new optimizations. The key is it's a toolkit for building new models, and also for checking that the models will work with the optimization, so we don't need to redo all the work every time we come up with a new model. Because otherwise, I'm going to come up with a new memory model, or I'm going to come up with some new setting, and I just need to redo all the work. And that was the whole idea behind MLIR as well, is to just reduce the duplication of work. Because otherwise, you have a variant of SSA for GPUs, and a variant for CPUs, and a variant for FPGAs, and no one shares anything, and we don't want that to happen.
All right.
So this is more about the models than the optimizations.
Thank you.
Yeah.
I have a question.
Yes.
It looks like Freyd categories are a bit more general than monads, but it looks like all your concrete models are monads. Is there a reason to?
Our concrete models are monads, and the difference is basically that Freyd categories don't necessarily have that higher order structure. And we take advantage of this in the paper because, so one thing that we didn't mention here because it was already very rushed is linearity. So essentially, we in our paper supported the ability to reason about linearity and basically relevant and affine effects. And when you do that, you can do more complicated things like separation logic, and making that higher order can be hard. And here you can reason about things that are difficult to make higher order. So, in this case, all the simple models are monads in like the Cartesian setting, but especially in the linear setting, you might have some more exotic models. Hello.
Well, in done world spaces will not be it. So, kernels,
Yeah.
What?
There's a model, there's an easy model,
Yeah.
that's important, that's not that model.
Yeah.
Okay. I think. Any other questions? Oh, yes.
Wait, did I do this way too fast?
I'm just